to talk about a problem that's kind of similar to a lab problem that you might encounter if you were actually in a physics classroom. The problem says that you've got students in a physics lab, and they're asked to find the length of an air column. It's a tube and it's closed at one end, which is important, and it has a fundamental frequency of 256 hertz. So the sound is being projected and you've got a resonance happening, 256 hertz, and they find it at 0.336 meters or 33.6 centimeters. The question asks, what is the temperature in the room and where will you find the second resonance? So this is kind of a cool problem because it makes us think about what standing waves in air columns that are closed at one end look like. And that's important because you're going to need to know that to solve the problem. So think about if you've got a standing wave and one end is closed, this end has to be a node because a node is where you don't have a lot of motion. A node is where you're at equilibrium. So this is still because there's no place for the air to move. You have a resonance when you've got the maximum motion at the very end of the column, and the maximum motion happens where there's an antinode. So the first frequency that you're going to hear, the first resonance that you're going to hear at this frequency is going to happen when you have one node and one antinode. And if you think about what a wavelength looks like, one node and one antinode is a quarter of a wavelength. So that's important. And this picture is going to be important when we do the second resonance. So let's figure out what the temperature in the room is, and then we'll talk about the second resonance. We've got this equation. It's for the speed of sound in air for a certain temperature. And we know that the frequency times the wavelength is equal to the velocity. So that information is going to give us all we need to figure out what the temperature in the room is. So you know that if you plug this in right here, you know that this length has to be 1/4 of a wavelength. So your wavelength is that times 4, or 1.344 meters. Plug that in and your frequency, and you get that the velocity of sound in the air in the room is 334 meters per second. Then you take this equation, work backwards to find the temperature, and you get that the temperature is 295 Kelvin, which is 22 degrees Celsius. And so that's the first part of your problem, 22 degrees Celsius. So remember that you've got a resonance at an antinode. So you know that this first length is 1/4 of the wavelength. Your second resonance is going to happen at your second antinode. So if you think about the picture of a wave, you know you have a node, an antinode, a node, and an antinode. That's not a full wavelength. It's 3/4 of a wavelength. So you know that the second resonance will happen at 3/4 of a wavelength. Since you already know what your wavelength is, you just plug that number in here, and you get that it's about 1 meter. So now you've done all of the work that you would have done in that physics lab, and helps you think about, remember this, this picture down here is key, what standing waves look like in air columns that are closed at one end.